Hi guys, and welcome back to Royan's Study Corner. I am Royan, and the aim here is to make learning as fun, easy and accessible as possible. Now, in our last video we would have looked at how to plot a graph, and we would have gone through in detail planning and plotting a graph from beginning to end. Now, question 1 of paper 2, after plotting the graph, usually asks you to find the gradient. Now, finding the gradient is pretty simple. There's a formula that we follow, but there are just a few small things that we'd have to tweak and a few things that we'd have to remember depending on the graph that we're plotting. So today we're going to be going through one of the graphs that we would have done last video and find the gradient of that graph. So let's get started and see how it goes.
Right, so here we are with our gradient of a graph. Now, what exactly is gradient of a graph? The gradient of a graph refers to, or the gradient of a line rather, refers to the steepness of the line. So that's why we use gradient and the slope interchangeably, because if you think about it, it's really just how steep this line is. And steepness is a concept that we are familiar with because we are used to thinking about it in terms of hills and that sort of thing. Now, gradient can be thought of as rise over run. This means how much is this increasing in height over a certain distance. We're going to use this to derive our formula for gradient eventually, but let's just think about that now. Gradient is equal to rise over run. Now, as I said before, we're familiar with using this when we are referring to a hill or some sort of incline, because we see here that our rise is this vertical increase and our run is across this distance. Now, if gradient is equal to rise over run, and in this case rise is 20 meters and run is 5 kilometers, which is 5,000 meters, then we know that's going to give us a very small slope, and this now means that this slope is not steep. It's a very gentle slope. You're just gradually walking upwards. Now, let's say that the roles were reversed. Let's say we had a rise of 20 meters and a run of 5 meters alone, so not kilometers, and you go up the hill. Then you'll see that the rise is still just as high, but it's over a much shorter run, only 5 meters run. So you can see then that that would mean that this hill or this incline would have a much steeper slope than the initial hill or incline here. So keep in mind rise over run, and I think that using the hill as an example always kind of keeps that in your mind, because it's something that you can always relate to a steep hill versus a gentle incline. Now, while we always say rise over run, we also have to keep in mind that rise means vertical change and run means horizontal change. So here we have a little sketch of what a graph may look like after we plot it, and we see that while it's rise over run, rise is vertical change and run is horizontal change. Now let's apply this to our graph that we may plot. So this will be a hypothetical graph that we may have plotted to see how exactly we get the formula for gradient. Now, we already said I've been singing the song since the video started. Gradient is equal to rise over run. And then we just saw in the last slide that rise is the same as your vertical increase or your vertical change, and run is the same as your horizontal change. But how does that get us to our gradient? Now, if we are thinking about our graphs, we'll know that vertical change refers to our vertical axis, which is our y-axis, and horizontal change refers to our x-axis. So vertical change is essentially change in y, and horizontal change is essentially change in x. Now if you look below that, you'll see this thing triangle y and triangle x. That literally means change in y and change in x, because this triangle here, we call it delta, and it's another Greek letter. You'll see Greek letters popping up in physics and in math in general all the time, and it really just means the change in something. So if you see delta y, it means a change in y. If you see delta x, it means change in x. That means exactly the same as this up here, but it's just a shorter form, so you may see that in textbooks sometimes, or you may just prefer to write that because it's much faster to write. So we went from understanding that gradient is rise over run to understanding that that is the same as saying that gradient is change in y over change in x. Now, what do we do with that? How do we apply that to our graph? If we look at our little sketch here, so let's imagine this is a graph that we plotted. We drew our line of best fit over here, and now we're going to try to find the gradient. Now, if we are looking at change in a quantity, change would mean that something happened. So something happened somewhere along the way. So if you got taller and we want to see the change in your height, we would look at your height now and take away what your height was before you started getting so tall. And in the same way, if we want to see the change in y, we would look at some sort of final value for y, so one of the latter values of y, and from that we'd have to take away one of the earlier values of y. And in the same way, change in x would mean we'd have to take one of our final values of x and take away from that one of our initial values of x. So if we look at this and we plot this graph and we say, okay, we have to take some initial values or close to initial and some final values or close to final to figure out what is the change in the y and what is the change in x. So we take 2 points, and this is the process that we'll go through every time we have to find the gradient of a graph. We choose 2 points, and we want 2 points that are pretty spread out across the graph. So in this case, we choose this point here, and we choose this point here. Now, the coordinate of this point now would be, since we don't have actual values, we'll have x1, y1, because it's the initial one, so we'll go with 1. And then here, again, we don't have a number for it, so we'll just call it x2, y2. So this can be thought of as our initial values, and this can be thought of as our final values. So as I said before, if we want to see the change in something, we'd have to take our final values and take away our initial values. And that's exactly what we do in this formula. We say change in y would be our final y value, our latter y value, take away our earlier y value. And change in x would be our final or latter value for x minus our initial or earlier value for x. So that's how we get this equation y2 minus y1 over x2 minus x1. And then we can see on this graph here, it's the same as rise over run, change in y over change in x. Now on any graph that you plot, you'll have actual values, so you won't have to substitute x1 or y1. You'll have a value, whether it's 2, 5, -6, whatever it is, and you'll plug those in, and that will give you a value for your gradient. So we know now how to find our gradient. Now there are different types of gradient that you'll see when you plot your graph. and it's good to keep them in mind, just so from looking at a graph that you plot, you could have a general idea what the gradient would be like there. And the first image we'll see uphill, or positive slope. So we see that this graph is increasing this way, and it looks like if you're walking up a hill, you're going up the hill. So if you are going up the hill, then technically that can be thought of as positive, so that slope would be positive. You're walking up and forward. And in the same way, the next one can be thought of as going downhill, so we have a negative slope. So if the graph is going up like it's walking up a hill, the slope is positive, or the gradient is positive. And if it looks like if you're walking down a hill, then the slope or gradient is negative. Now sometimes you'll end up with a completely horizontal line, so there's no tilt in that line at all. It's completely horizontal, it's parallel to your x-axis. If you just look at it, you realize that line is flat. And if a line is flat, it means it has no slope or steepness, so it's just zero. Now our final type that we'll see is a vertical graph. So if it's completely vertical, this means that whatever x is here, if x is 4, x will continue to be 4 going up for each value of y, regardless of what. It's just a perfectly vertical line, so your slope is undefined. So if it's leaning forward, it's positive. If it's leaning downward, it's negative. If it's horizontal, it's 0. And if it's completely vertical, it's undefined. So then if you look at a graph, most of the graphs that you'll plot will look like this. So then you'll know right off the bat, okay, my graph is going to have a positive gradient. So if when you substitute values in, you're seeing a negative gradient, even though your graph looks like this, then you know something is wrong somewhere and you need to check over your working. Now another possibility that happens sometimes, it's not in contradiction to this, but sometimes rather than a graph passing through the origin like what we would have had in our last video, sometimes it will just cut the axis somewhere else. So we're used to graphs that cut at the origin, so it intersects where y is 0 and x is 0. But sometimes it will intersect along the axis, just like this here. So you see this, rather than passing through the origin, it cuts the y-axis where y is equal to 1. So that in this case is your y-intercept. But calculating the gradient will be exactly the same. You'll still take your x1, y1, x2, y2 and find your gradient. So it's just something to keep in mind, that while most of our graphs will pass through the origin, there will be some graphs that cut our y-axis, and it's possible to cut your x-axis as well. So keep that in mind and just pay attention to what graph you're plotting, what are the quantities you're plotting, if it makes sense for it to pass through the origin, or if it's impossible to start at 0, so it will cut one of the axes. So we've looked at what gradient is in its general sense. We've derived the formula and the types of gradients that you'll get as well. So now we're going into the specifics for how exactly we calculate the gradient. Now, just like we did when we were deriving the formula, we choose 2 points on the line, and note here that it says these 2 points must be as far apart as possible. Because if you think about something, if you're going to do any sort of sampling, you want to kind of have a big range to take from. You're not going to have a whole graph and take one tiny section to find the gradient. And in bold here, you'll see these points must be read off from the line and not be plotted points. Now, this is one of the biggest things that I see students do all of the time. You have your graph, and on this graph, you have these points plotted. Do not take these points to calculate your gradient. take any random point along the line here. Do not choose points that were given to you. Read off 2 points from on your line of best fit. Now when you choose these 2 points, you draw a horizontal line from the first point and a vertical line from the second point. So it's essentially your rise over run type triangle. And it says that the hypotenuse of this, and you know that on a triangle the hypotenuse is this longest side that's right opposite the right angle. So this part of the line must be greater than half of your plotted line. This comes back to the same thing where you want a large sample size. You don't want one tiny space or one little triangle going from here to here to calculate your gradient. And then you finally plug these points into the formula. So whatever values you had here, if let's just say here some pretend values, we had 2 and 3, and up here we had 7 and 14. Then this will be x1, y1, and this will be x2, y2. So you'd plug these values into your formula. Note that when you are finding the value of the gradient, make sure to put in your units. So if you just have y here and x here, you have no units. But what about if, let's say for example, with our last graph, or the graph that we plotted for the last video, you have voltage in volts and current in amps. And if you're looking at the change in voltage over the change in current, then your units will be the unit for volts over the unit for current, so volts per amp. Now we're going to try this afterwards anyway, so that's okay if it seems a little bit abstract right now. We're going to put this into practice right now. So let's try this on a basic little graph here. That is not a graph that we plotted, it's just a worksheet that I got from mathdrills.com, so you can check it out and see. I'll put a link in the description box so that you can get even more practice and cool worksheets from them for all different types of things, because this is actually a math worksheet that I'm using here, not a physics worksheet. So you'll see how things overlap in math and physics, because in math you still have to find the equation of a line and that sort of thing. So that's where these things come in handy. So let's look at how we choose our points. So let's do this one as our example. We have this graph here. We have this as our slope. If we look at it right off the bat, we can see it's heading downhill, so we know our gradient must be negative. If it isn't negative, then I know I did something wrong somewhere along the line. Now first thing we have to do is choose 2 points from on this. Now generally you try to choose points that make sense to read off, or that's easy to read off. So avoid choosing points like this here that it doesn't actually hit the corner of the line, so then you have to approximate, and once you start to round off, you are introducing errors, which means your value will get further and further away from the actual answer. And if you're doing some research something, then that's bad, because it means you won't get the actual value of whatever you're looking for. And for the purposes of CXC, you have a certain range that you're allowed to be in. So if the actual ideal value is say 9.8, while everyone may not get 9.8 exactly, because we know there's a room for error with your line of best fit and that sort of thing, there is only a small range. If the answer is supposed to be 9.8 and you get 9, then technically you're wrong. That is too far from that. So always choose points that are easy to read so you don't have to approximate. So I'm going to choose this point, and the x value for that is -5, and the y value for that is 8. And I'm going to choose down here now, because this point is exactly on 2 lines. I'm going to choose that point. So here x is 5 and y is 0. Now I'm going to do my triangle connecting the points. So I've chosen 2 points, have done my triangle. Now I'm going to plug this into the formula. And we know the formula is gradient, or if you choose to put m, that's correct as well, is equal to change in y over change in x, which is the same as saying y2 minus y1 over x2 minus x1. Sometimes when students see values like this, they are unsure of which one to put as y2 and y1, and I would advise that you always start from left and move to right. So whatever you see on this general side of the graph or closest to the left, whichever point is closest to the left, choose that as your x1, y1, and whichever one is closest to the right, choose that as your x2, y2. So then in this case, we'll have x1, y1 and x2, y2. So y2 is 0, take away y1 is 8, and x2 is 5, and x1 is -5. Now pay attention to your signs here, because if I'm not careful, I could have just put 5 minus 5, because there's a minus sign here anyway. But I have to make sure and pay attention that to the fact that it's -5, so it's x2 minus x1. It's just in this case x1 is -5, and if you don't notice that, then your value will be, well, incorrect really. So if we look at this, we see 0 take away 8 is -8 over 5 minus -5. Once we see a minus and a negative sign like that, that's the same as plus. So 5 plus 5 is 10. So we have -8 over 10. Or we can choose to simplify that and put it as -4 over 5. Or we could choose to simplify that and say -0.8. And that is our gradient. We don't have any units here, so we don't have to write any units in to check to see what it's supposed to be, because it's just x and y. So our slope here is -4 over 5. Now let's look at our actual graph we would have plotted last video. So this is the graph of voltage against current that I plotted last video. So what I'm going to do now is I'm going to go through the process of finding the gradient of this graph. Now I'm going to zoom up here to look for points that are easy to read from, because they cut the lines at sensible places. Now I'm going to choose up here, I'll choose this one because it's exactly on the line there, and that will be, let's see, what is that point? 0.81234, so 0.84, and my y value is 1.8. Now let's look for a value lower down here, and I'm going to choose this point here. Oops, this point here. So my x value for that will be 0.1. 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, 0.17, 0.18. So 0.18, and my y value is 0.4. So remember, whatever is on the left side, that's our x1, y1. So this is x1, y1. And what is on our right will be x2, y2. So now we have these values. Now let me draw my triangle. So now you all are going to have to see the horror of me fighting up with this ruler here again, and hopefully being able to draw a straight line. And it is not straight, but that will have to do. So technically this would have been wrong, so don't follow me with that, because if you look closely you'll realize it isn't exactly on the line. It was actually supposed to be like up here. But then better I just not use the ruler and do this freehand, because I feel like my freehand lines were better than the lines with the ruler. So I'm very surprised with my lines there, and my vertical lines now. So this is my triangle. Now remember, our formula is gradient, or m, is equal to change in y over change in x, but we don't have x and y here, so in this case it will be change in voltage over change in current. So it will be the same as usual, y2 minus y1 over x2 minus x1. Now I'm using y2 and y1 because it's just easier for us to remember, even though technically it's voltage and current. So our y2 is 1.8 minus our y1 is 0.4, and then our x2 is 0.84, and our x1 is 0.18. Now if I plug that into my formula, into my calculator, sorry, I get, let me see, 1.8, take away 0.4, divided by 0.84, take away 0.18. That gives me 2.12. So my gradient for this graph is 2.12, and since it's voltage over current, and we know the unit for voltage is volts and the unit for current is amps, it means that my unit must be volts per amp. And that's how we calculate our gradient. So you see, now we would have plotted our entire graph, calculated our gradient, and we would have been able to get a good chunk of that 25 marks for question 1. So I hope this was informative and you all enjoyed it and were able to follow along all of the steps, and that it helps you all when you are plotting your graph and calculating your gradient. So that's it for this video. I'll see you all in the next video. Remember to stay safe and be kind to yourselves. Bye everyone.